We're going to be looking at motion in terms of the forces that cause objects to move and related to Newton's laws. Isaac Newton was a very popular scientist and very renowned scientist because he came across a lot of different science such as colour theory. We know about Newton's laws of motion, and we're going to be exploring Newton's first law of motion today. And I just did it recently with my Year 10 class, and we used a lot of everyday experiences to explain the fundamental concept behind Newton's law. And his first law is also known as the law of inertia. Let's write it down. Well, that's a bit of a mouthful, so let's read it through and dissect this a little bit. An object at rest will remain at rest, and an object in motion will remain in motion. But before I read the second half of the statement, let's just look at the first one. An object at rest will remain at rest. So I've got this pen in my hand. Well, let's do the ball. I've got a ball in my hand. That ball will remain at rest in non-motion at all, just sitting there, because at the moment all the forces on it are balanced. And the understanding that before we get to Newton's laws is about balanced and unbalanced forces. So at the moment, the forces acting on this ball are balanced. So if we could draw that ball, this is what we would see. There's the ball, and we have the force of gravity acting downwards. So we go F for force, put an arrow on the top because it's a vector quantity. It has magnitude and direction. And we put a little lowercase g there to represent gravitational force acting downwards. Well, since the ball was not moving down, it was stationary, it had to have a force acting upwards. And you could say that the force was applied by my hand holding it up. So an applied force. So we could put an A for applied force. So I was holding that ball up. And so those forces are equal and opposite, even though I've drawn that a little bit bigger, but that's just the way it happens at the moment. So the ball was at rest, it wasn't going anywhere. If I was to remove my hand, that ball now would remain stationary, because it says an object at rest will remain at rest. But then, of course, it says, until it is acted upon by an unbalanced external force. So if I remove this upward force of holding the ball, the only force now acting on that ball is the force of gravity, and that's going to pull it down, which means we have an unbalanced force situation here. There's force going down, but there's no force going up. So it's unbalanced. And so that ball is going to be accelerated downwards. So that's the at-rest portion. Let's look at the in-motion portion. It says an object will remain in motion in a straight line until an unbalanced external force is added to it. So if I could get this ball and I could throw this ball in space, and if I threw it in space, it will be going in a straight line forever, because it will remain in motion in a straight line. And in space, it's a vacuum. There's no air or resistance at all. It's a vacuum, so it's keep going. And it will keep doing that until an unbalanced external force causes it to change direction. Now, that could mean that it collides with something, like it might collide with an asteroid or something like that. It might be going near a planet, and if we pretend this ball now is a planet, and here comes the ball in a straight line, its gravity is going to cause this to change its direction. So it's going to pull it down towards the planet. And it only changed direction from a straight line because of this unbalanced external force, the gravity of our pretend planet. So all sort of objects, their motion can be explained in terms of this. You experience it all the time. You're in the car, you're going in a straight line. If the person driving the car was to slam on the brakes, the car comes to a stop, but you will keep going forward because it says an object will remain in motion in a straight line until an external force causes you to change that. So you slam the brakes on, you keep going forward, but you have a seatbelt on. That seatbelt provides a force that will stop you from being propelled through the windscreen, right? And that's why we wear them. So we did some explorations today of looking at different aspects of Newton's laws. So what I want to do is I'm going to put those up there, and we're going to talk through them to see how they illustrate Newton's first law, and we're going to relate it back to this statement. So here we go. The first one, you can see there's a quick little video of what I like to call the good old coin drop. You put some coins on your elbow and you move your elbow out of the way. And as you can see here, and we're going to put it in slow motion, that those coins remain stationary. So here are the coins like that. And here's my elbow, or not mine, but just an elbow, right? And while they're there, we've got a downwards force on those coins, the force of gravity. And we have an upward force acting on that provided by my elbow. And you will learn, and when you do more science, that that's called the normal force, right? So we write a capital N for normal force. But the forces are balanced. And if the forces are balanced, those coins aren't going anywhere. They're going to remain at rest. But when you move your arm out of the way, so a second or two later, right? Let's try and keep the colours the same if we can. The coins are there, and now your elbow is being moved away from those, right? So we put a little V to say we're moving our elbow away. Those coins will momentarily remain at rest because of this thing called Newton's first law. In fact, it's due to something called inertia. And inertia is a property of a substance. It's the property to resist motion. In other words, it's a property of a substance that keeps it at rest or in motion unless this external force is applied. So it's a resistance to movement, this thing called inertia. And it's a weird concept to try and get ahead in your head, but the more we talk about it, the more you'll understand what inertia is. So these coins are staying there because they have some inertia. They have a resistance to movement. But it only happens for a microsecond until this unbalanced external force causes it to be pulled downwards. Of course, that is the force of gravity. There is no upward force now on those because you've removed that. You removed your elbow. So the only force acting on those coins is the force of gravity, and they fall down. But of course, your reaction time is so quick that you can catch it. And you can see that in the video with the student there catching them. So that's the first one, the good old coin challenge. Let's do another one. All right, this is a classic. All right, an oldie but a goodie. And this is the good old egg drop challenge. And with here, we've got a glass or a cup full of water. Then we put a tray on top of that. Then on top of the tray, we put a cardboard tube, and then we put an egg in there. Now, of course, at this moment in time, all the forces are balanced. The egg is stationary. It's got this downward pull of gravity acting on it, so Fg for gravity, but it's also got an upward force of the carton. The carton is providing an upward force on the egg, and that is going in that direction. So the applied force, which we just said we called the normal force before. But the main idea here is that upward and downward forces are equal. They're balanced. So since they're balanced, in this case, the egg is not accelerating. Okay, it's stationary. But if we hit the tray that way, this tray is going to go flying off in one direction. This lip is going to hit the cardboard. And if we do it just right, this egg should spin in the air or move in the air at that location. It should stay because it initially was at rest, so it's going to remain at rest until we have, and I'll just try and draw this egg on the side here because it's spun around a little bit. And then, of course, the only force acting on it is the force of gravity, and that pulls it into the water. And as you can see there, the student was successful, right? The powers of the universe was agreeing with our classroom at that moment, and Newton's laws were too. So that's a classic one, the good old egg drop. Let's look at another one that relates this, because this one shows what happens when an object is at rest. It remains at rest just for a microsecond until an unbalanced external force causes it to change its motion. And when it changes its motion, it accelerates. Okay? So rather than saying fall, we're going to say it accelerates. Because it's not traveling here and all of a sudden it's accelerating downwards. So we're saying that the egg has now got unbalanced forces, and when the unbalanced force occurs, we have acceleration. So remember that. Unbalanced force causes an acceleration, and so the egg accelerated. Let's do another one. All right, another scenario that we did in class as we looked at how objects remain in motion in a straight line. Well, as you can see with this one, this was like the trolley challenge. You get the trolley and you push the trolley first just with your foot. So here's a trolley. You push it with your foot and it travels in a straight line. You can see in the video the student pushed it, traveled in a straight line. Okay? Nice and easy. Remains in a straight line until an unbalanced force causes a change in its motion, and that is, it decelerates. So when the trolley is pushed, we've got a bit of air resistance, we've got friction between the wheels acting in the opposite direction to motion, and so therefore the trolley accelerates in a negative way, and we call that deceleration. So the forces were unbalanced and it slows down. But then we had a student sit on top of it, and the student was pushed and the same thing happened. Even though we had more mass, right, it still did this, it still followed Newton's laws. It remained in motion and it stayed in a straight line until an unbalanced force caused it to accelerate. And so when the student was pushed, it was accelerating in a negative direction and in a negative manner. In other words, acceleration was decreasing, and so we call that deceleration. So the student was showing that Newton's law is true. Okay. Now the difference between the two, of course, is its mass. Without the student, it was very light. Without the, it didn't have much mass. With the student, it had lots of mass. So the inertia was more when there's more mass, right? So an increase in mass causes an increase in inertia, and therefore a greater resistance to change. Think about it yourself. You get a car, take the handbrake off the car, and you try and push the car. It's very hard to push the car because the car has more mass, therefore it has more inertia, therefore it has more resistance to change its motion, right? So the more mass, the more inertia, the harder it is to change its motion. So that one there was showing us about straight line and unbalanced forces causing it to slow down. Well, what about this next one? This next one's a similar sort of thing. You can see there it's a soccer ball. It's a hover ball as the pen falls to the ground. It's a hover ball. And so there's the side-on view of my hover ball. It's producing air. That air is reducing the friction that it has with the ground. And so when I apply a force to that hover ball, that continues in a straight line. So its motion continues in a straight line until an unbalanced external force causes it to stop. Well, that could be when it hits something, it'll stop. When it falls off the desk, it'll stop, because that's the unbalanced force, gravity pulling it down. And even though we have got a cushion of air there, it still has a little bit of friction because it's not a perfect cushion of air. And we also have air resistance in the air pushing this way as well. That's going to slow it down so that the hockey puck or the soccer ball will slow down. Okay, but it is illustrating that an object in motion will continue in a straight line until it's acted upon by an unbalanced force. The last one is a really cool one. It's where we get a tray, and on that tray we place a cup of water. And we spin that tray around in a circle, and we try to explain what's going on there with Newton's law. Because a lot of people think that there's this outward acting force called centrifugal force, and it's that outward acting force that pushes the cup onto the tray. No. Centrifugal force is not really a force. It's known as an apparent force. It feels like it's there, so when you're going really fast around a corner, it feels like you've got this force pushing against you, against the side of the car or something like that, but it's really just you changing direction because of the law of inertia. So as you are going here, let's say you're sitting in a car, that's you in a car by the way, you want to go in that direction nice and straight, but the car starts turning a corner. As the car's turning a corner, you want to keep going straight, but the side of the car's pushing on you, and so it's changing your direction. And it feels like to you that you're being pushed into the side of the car when it's actually the car pushing into you. And we'll learn a bit more about that when we talk about Newton's third law. But it's this Newton's first law, this law of inertia, that's causing you to be pushed against the side of the car. So when this cup full of water is changing direction, this water is being pushed to the side of the cup throughout its entire journey. And so as long as you're taking that around in a circle, the water is always being pushed against the side of the cup and of course the bottom of the cup, and it's not falling out. And then when you get round, you slow down so that you don't spill it everywhere. There's some quick little demonstrations of experiments to illustrate Newton's first law of motion, the law of inertia. So next time you ride your bike and you're riding really fast down a hill, just make sure that you don't hit your front tire onto something that's a big rock, because your bike is going to stop, but you are going to keep on going in a straight line, straight over the handlebars, and it could be a little bit perilous to your skin, right? Scratch it off your body, not what you want. Anyway, hopefully Newton's first law makes more sense. See you in the next video when we talk a bit more about his second law. Okay, see you then.